All right, let's start with a little comparison here. Take a look at these two images. Now, both of these are X-rays of the exact same piece of soft tissue, but wow, look at the one on the right. It's incredibly detailed. You can literally see structures that are completely invisible on the left. So what's going on? How can one X-ray see what the other misses entirely? Well, the answer is a revolution in imaging that's been more than 100 years in the making.
So that's what we're going to dive into. We're going to break down the science behind these amazing images. We're talking about a technology called phase contrast X-ray imaging. And believe me, it is fundamentally changing the game and how we see the world, from the inside of our own bodies to the batteries powering our devices.
To really get this breakthrough, we first have to go back, way back, to the beginning and talk about a fundamental limitation, a blind spot in the X-ray technology that we all know.
You know, the X-rays you get at the hospital work in a pretty simple way. They shoot X-ray photons at you and see which ones get absorbed. It's basically like casting a shadow. The dense stuff in your body, like bone, blocks the photons and creates a dark shadow, while the less dense stuff just lets them pass right through. And this works great for high-density things like bone or metal, no problem there. But for materials made of lighter elements, what scientists call low-Z materials, it's a whole different story. Your soft tissues, plastics, and even advanced materials like carbon fiber are almost totally transparent to traditional X-rays. And that's why they just show up as these blurry, indistinct smudges. And the physics behind this is kind of wild. The visibility, the contrast you see, depends on an element's atomic number raised to the 4th power. That's a huge relationship. It means that even a small drop in how heavy an element is causes its visibility on an X-ray to just plummet. This right here is the X-ray's blind spot. So how do we see inside that blind spot? Well, the answer is to stop looking at the X-ray's shadow and start measuring something completely different about the beam itself. So instead of just checking if the X-ray got absorbed, we can look at how much it bends as it passes through something. This bending is called a phase shift, and you've seen this a million times. It's the exact same reason a straw looks bent when you put it in a glass of water. The light waves are literally being distorted as they move from the water to the air. So here's the absolute key to all of this. An X-ray wave has two different properties we can measure. First is its intensity, how much of it gets absorbed. The second is its phase shift, how much it bends. And for more than 100 years, we pretty much only paid attention to its intensity. But here's the kicker. For all those low-Z materials, the soft tissues, the plastics, that phase shift signal is up to 1,000 times stronger than the absorption signal. 1,000 times! We were basically ignoring a signal that was 1,000 times better for seeing the very things we couldn't see. Now, this idea was totally revolutionary, but for decades, it was pretty much just a theory. Actually being able to measure this tiny, tiny phase shift, well, that required a very special kind of light. And a very, very big machine. See, the problem was, to actually see these phase shifts, you needed an incredibly pure and parallel beam of X-rays, what physicists call a coherent beam. And for a long, long time, the only places on Earth that could produce a beam like that were synchrotrons, these massive particle accelerators the size of sports stadiums, just huge. And get this, it took a full century after Röntgen's discovery for the breakthrough to finally happen. In 1995, a team led by Anatoly Snigarev at the European synchrotron used one of these coherent beams to prove it was possible. They saw that if you just let the X-ray wave travel a little bit after it passed through a sample, the phase shifts would naturally turn into visible patterns, lighting up edges that were totally invisible before. It was incredible. And then, just 4 years later, Peter Clotens figured out how to turn that trick into full 3D images. But this created a whole new problem. This amazing, world-changing technology was trapped inside just a handful of multi-billion-dollar research facilities. So the next great challenge was to set it free. And that's where researchers like Professor Alessandro Olivo and his team at University College London come into the story. They basically spearheaded the mission to take phase contrast imaging out of the giant synchrotron and shrink it down into a machine that could fit in a regular hospital or a lab. And their solution was just so clever. It's a technique they called Edge Illumination. So instead of needing a perfect coherent beam, they just used two simple masks. The first mask takes a normal, messy X-ray beam and chops it up into thousands of tiny separate little beamlets. Now, as these beamlets go through your sample, they bend. Then, the second mask, which is placed right before the camera, is just slightly out of alignment. So how much a beamlet has bent determines how much of it can sneak past that second mask. It directly translates that invisible bending into a change in brightness that the camera can see. It's brilliant. And this solution is just so practical. It works with the same kind of messy X-ray tubes you find in every hospital in the world. It's really efficient with the radiation dose, which is great for medical use. And maybe most importantly, it is incredibly robust. You can misalign the masks by up to a millimeter, which in the world of optics is a gigantic error. And the image quality barely even changes. This was the breakthrough everyone was waiting for. It was the key to democratizing the technology.
So now that this technology is out in the world, what can we actually do with it? Well, the applications are just breathtaking.
In medicine, it's allowing for something called virtual histology. So imagine you have a very delicate, maybe an irreplaceable tissue sample. Instead of physically slicing it up into tiny pieces for a microscope and destroying it, you can create a perfect, high-resolution 3D digital copy. Then researchers can fly through it, slice it any way they want, as many times as they want, all without ever touching the original sample. This is already giving us incredible new insights into everything from lung disease to how a fetus develops.
It's also transforming engineering. I mean, think about the phone or the laptop you're using right now. One of the biggest safety risks in their batteries is the growth of these tiny lithium spikes called dendrites. They can cause fires. The problem is, lithium is one of the lightest elements there is, so it's totally impossible to see with a normal X-ray. But with phase contrast, now, for the first time, researchers can watch these dendrites growing in real time inside a working battery, which is crucial for helping them design safer, better ones for all of us.
This technology is also literally rewriting history. Archaeologists can now peer inside ancient metal artifacts and see the delicate organic materials, like fragments of cloth or wood, that have been hidden and preserved inside for centuries. They can look inside a fossil without ever having to break it open, unlocking secrets that have been trapped in stone for millions of years. And in high-performance engineering, we're talking aerospace, that kind of thing, it's a complete game changer for non-destructive testing. It can spot tiny but potentially catastrophic flaws, like microcracks or gaps between the layers in a carbon fiber composite that a conventional X-ray would completely miss.
So when you take a step back, you realize we've gone through this fundamental shift in how we see things. For 100 years, X-ray imaging was all about seeing the shadows cast by dense stuff. But now, by measuring the subtle bending of light waves, we're able to see the very fabric of matter itself.
This technology is really giving us a whole new set of eyes to look at the world, revealing a level of detail we just never thought was possible. And it leaves you with this really fascinating question, right? Now that we can finally see the invisible, what other secrets are out there, just waiting for us to discover?